So good afternoon and welcome to the second part of this session on design of sensor system and advanced sensor technologies. This session started yesterday with 2 oral presentations and 11 poster previews. Today we'll have 5 oral presentations and 18 poster previews. There was a 15 minutes discussion that was scheduled at the middle of the session, but instead of that, we might take 1 or 2 questions at the end of each presentation and also save time for the poster previews at the end of the session because it might take more than 15 minutes. So we'll ask maybe the 2 last presenters to get ready, maybe to present a few minutes ahead of schedule. So in this session, as we said yesterday, we try to cover all IMS technologies, some OSI technologies as well. Yesterday we talked about seismic, infrasound, and today we'll talk about seismic again, radionuclide, and maybe mainly noble gas, and OSI technologies as well.
Okay, the first presentation is going to be the one from Mr. Guralp. Its title is Performance of Multi-Parameter Borehole Instrumentation System at Mars Site.
Okay. Good afternoon, everyone. I hope you have a great lunch, and in this palatial place, it's a privilege to be able to talk to you all. What I'm going to talk about is really nuts and bolts of a seismic system rather than anything sophisticated. What I want to talk about is 2 boreholes co-located side by side and instrumentation that we installed in these 2 boreholes, which is multidisciplinary. And it's been running since 2016 or 2015. The site is in Turkey, a place called Tekirdağ. The name of the site is Mars Site, and it's located right there, which is right next to the Anatolian fault line, very close to the sea and very close to the fault line. The idea is to not only to understand how the fault line is moving, which is not my side of the story, but the idea is to be able to install instruments so as to get best out of from a very, very difficult site, and to try and compare such a site to some of the best land-based systems, which tend to cost quite a lot in terms of installation and maintenance. The instrumentation that we installed in these 2 boreholes there are quite a number of them. It's difficult for me to go through all of them simply because of 15 minutes. But we have 2 boreholes side by side. They're 150 meters deep, and they're 4 meters apart from each other so that we can study 2 instruments which are co-located in a borehole, which I don't think actually exists anywhere in the world, as long as someone can correct me. Within one of the boreholes, we have a very high precision tilt meter, and in one of the boreholes we have a strong motion sensor, which is from Guralp, and a very broadband 3TB, again a broadband velocity sensor, but modified so that not only it's very broadband, meaning going down to 360-second period, but the high frequency end goes all the way up to 150 hertz. So the instrumentation installed is genuinely sophisticated. And the idea is that what can we do with this? There's lots of other types of devices in there, such as digitizers and power supplies. But in addition to the broadband instrument, we've also installed a dilatometer. And the design of the dilatometer is brand new in the sense that it's intended to be a high-frequency dilatometer as well as being a long-period one, meaning it's a DC coupled all the way from earth tides to creep to the deformation, but all the way up to 30 hertz to understand how a dilatometer compares to a short-period instrument. To show that, I'm just going to literally go through the setup. Now, most boreholes that CTBTO or anyone has tends to be full of water. The idea here is that we wanted to have a borehole which is dry, completely dry. And trying to make a dry borehole, especially right next to a sea, next to a stream, is not that easy. So we had to devise a technique. A technique had to be cost-effective, and the technique is very simple in that we decided to use effectively pressurize each section of the borehole before it was installed. It was effectively pressurized with a little bung, and then we welded it together before it went down. But having pressurized it after welding, We just used some soap, just washing soap, to see if it bubbled, and I can assure you it worked very well. So it's a very simple technique one should use everywhere. I was there whilst this was being done. It took about a day and a half to install 150-meter borehole. Now, each section of the borehole is about 8 meters long, as you can see there. And at the bottom of it, we decided to install the dilatometer. Dilatometer is an extremely sensitive device. It has literally 2.5 to 3 millimeter thick casing. And in order to install that, we had to do effectively a cage. You can see the cage being there. And this cage was welded at the bottom of the borehole, and you can see the dilatometer in there. And the dilatometer is a 3 meter, I mean, there's so much to talk about, but it's 3 meter length oil-filled device, which has effectively a displacement sensor, which measures the displacement or the expansion of the oil within dilatometer. So in order to, of course, get the cables out, this is practical side, which is very important. We had to actually put sort of tubing on the outside where the dilatometer cable came out. More importantly, in order to understand that the dilatometer would work throughout, we actually operated the device as we installed it. And that took about, as I said, a day and a half. And of course, in order to penetrate into the formation, we had to have a reasonably strong end, but the dilatometer certainly survived. So that is the basis of the instrument. The next phase, of course, in any borehole is the cementing or grouting of the borehole. In this case, unlike all the other boreholes where the boreholes tends to be grouted from in outwards, we grouted it from out inwards, so to speak, so that we've used effectively 3 plastic tubing which were attached to the outside of the casing as it went down. 2 of the black ones you can see here were all the way down to sort of about 150 meters. And then the blue one was left to be somewhere halfway, so about 75 meters. So once the whole casing was inside the drilled borehole, the cement was effectively injected from outside, and it came out to the top, all the way from bottom to the top. And we think we really, really have cemented or grouted the instrument properly to our casing. And actually this shows, especially when you look at the high-frequency performance of the instrument. The site is very simple in terms of civil works. The boreholes are effective. They come out about 30 centimeters from the bottom of this section. There are 2 of them side by side. Very simple installation, all suited to sort of the environment that we found, and also, of course, the budget we had. And you can see the power coming in, and we have all the necessary instrumentation to transmit the data to different locations. The first thing to show from a very broadband VBB, 360-second period, to, let's say, 150 hertz is really earth tides. If you really want to have a broadband instrument which looks at long period, I think it should be able to detect earth tides. And here is, 8 days of earth tide data from vertical sensor. This is velocity. And you can see the different teleseismic events, and that is the large Japanese earthquake, which was detected at Mars site. So the instrument is stable, and we think without centering the instrument, it will take possibly 2 years before one needs to center it. But more importantly, when we compared 1 year of data of when it was inside a wet borehole, and 1 sort of year of data when it was in the second borehole, which was dry, you can really see the differences, especially in long period. And it's pretty clear that putting a little bit of effort and that extra time, not expense actually, just time, which might be expense for you, some of you, that really makes a huge difference as far as the performance of the instrument in the long periods. Now, to look at it in slightly in a different way, and this is a 4-hour section of a dry borehole, 4-hour section of wet borehole, low pass at 100 seconds, and I'm getting rid of all the high frequency stuff, which is mostly what you would be interested. You can see the enormous difference in the time domain, and the frequency domain, it's even more apparent. And you're looking at the frequency domain, you can see that the broadband VBB sensor at 150 meters deep, now I'm sure you're all aware, that's the low noise model, which has been around long time, or the new low noise model. And that is the power spectral density of the instrument, the VBB instrument. I think it's 4 hours or 2 hours 2 hours of data, whilst the red one is a surface instrument that we installed right above the borehole. You can instantly see the difference in detection ability of broadband sensor in a borehole, broadband sensor on the surface. Now, in order to understand how important it is, I think, for a good site from a sort of a noisy site, I've decided to use the Columbia College seismic station, which is equipped with one of the fantastic instruments, STS-1s, and strong motion instrument, and all insulated. You can actually see the insulation, the amount of effort is taken to install this instrument in vacuumed flasks. And from this, you can get a fantastic instrument. And this is, this is from Barbara's lecture notes. And you can see that the earth modes can be easily detected from a quiet site, which is what you need in order to really have a good broadband station. You need to be able to detect such small signals. The rest of it is quite easy. Now, in order to compare it, I certainly don't have the same data set, but looking at from Mars site, this time it's 17 days of continuous velocity information. And there was an event in Ecuador. And if you actually look at the Earth modes from Ecuador event at Mars site, it is spectacular compared to many stations. So a borehole, 150 meters deep, very broadband sensor, installed in the most, I would say, seismically active region, you should be able, one can get a station as good as Columbia University land-based setup, which is very, very quiet. Now, having said that, I mentioned the dilatometer in order to compare the two together. The dilatometer is effectively, I mean, this will take maybe a day to talk about, but is effectively an oil-filled reservoir, and we have quite a number of sort of electronics, but I've used, unlike any other dilatometer, a capacitive sensor to detect the actual expansion of the oil. And just to show you the capability of a good broadband instrument and a dilatometer side by side, and I don't think this has ever been done before, co-located, very broadband sensor with a dilatometer. You can see that the mass position, this is another output from a broadband sensor, which is in white, and then the dilatometer was just installed. As it stabilizes, you can see how the earth tides, these are earth tides, these are the 12-hour period per day, how it actually synchronizes itself, and this was literally installed at the time, showing that a dilatometer, in this case, was DC coupled, working and it's a form of calibration, of course, working down to DC and also able to detect in a stable environment earth tides. And in this case, I think this was maybe a couple of days later, you can see expanded version of the similar output. This is vertical mass position, and the green is the dilatometer, literally raw output, DC coupled, sample to 1 samples per second. I don't know much about the mathematics of this, but it appears as if even though it's a horizontally organized instrument, the mass position from vertical seems to correspond very well to the dilatometer output. Now, if one looks at the dilatometer, in this case, as a broadband sensor, short period and a long period, and compare it to the broadband velocity sensor co-located in the same borehole, you can see that, and I've sort of used the same transfer function for dilatometer as I use for the the broadband sensor. You can see that it really does fit very well around teleseismic, around microseismic region. It fits extremely well all the way up to maybe 20, 30 seconds. And of course, because it's DC coupled, dilatometer possibly drifts compared to broadband sensor, which is following the low noise model. And the high frequency end, of course, 3T or the borehole instrument is doing far better. but you can see the similarities. And this is in frequency domain. It needs a lot more work. I'm not capable mathematician to be able to do this, but 2 minutes. But if we look at it in a little bit more in detail on the long period side, again comparing the dilatometer to vertical instrument, again the comparison at sort of the microseismic region, 6-second period, to up to 20, 30 seconds is quite remarkable. Now, I thought I should also show some traces of seismic information in that if you look at sort of vertical north, south, east, west from a broadband sensor, these are reasonably small signals, distant events. But here's the dilatometer. The onset, the arrival of the actual signals is clearly there, including the tilt meters. This is X and Y tilt meter. It's co-located at the same spot. Now, if you look at the similar signals, this time from broadband dilatometer tilt meters, this time an event in Italy and reasonably close, you can see that it really does make a lot of, I think, sense to maybe look at dilatometer as a short period instrument as well as other types of measurements. And in this case, which one is this? Sorry, this is in this case where I wanted to show that, by the way, the borehole also have a strong motion instrument to show that the dilatometer works, that the of course strong motion instrument also is there, and also we have the broadband sensor, including the surface unit. And just to give you a very simple summary, what we want to achieve at Mars site, I think without I think we have managed it in that we have extended, and I'm sure you've seen this type of plot many times. I've got this from Iris Pascal's presentations, in that we've got a strong motion sensor, which is Guralt 5TV, which covers all the way up to, let's say, 100 hertz. And we have 3TB modified broadband sensor, which we extended all the way up to 150 hertz. And it goes all the way up to earth tides without any difficulty. In addition to that, we've added a tilt meter and a volumetric strain measurement, which really expands this plot in a reasonable way, both in the short period, the high frequency, and in the long period end. Thank you very much.
So we might have time for 1 or 2 questions.
I have one question. Jonathan, thank you very much for impressive presentation. It really extends the horizons of the applicability of the broadband instruments. Thank you very much for that. You mentioned about the north, south, and east, west components of the horizontal components of the instrument. How you did the orientation of the broadband instrument down in the borehole?
Okay, so again, it shows my age probably, but when I was doing my PhD, we went back to understand how you organize, how you actually orient a broadband instrument in a borehole. Because in the past, I think Teledyne Geotech had wonderful instruments. They were using gyroscopes, which in itself is expensive, complicated method. At the time, Ron Birch at Blackness Seismological Center in England, who was working with me, we decided to correlate microseismic peak on surface to the microseismic peak you detect from a broadband instrument. Of course, it has to be broadband. You can't do it with you can't do it with a short period instrument because microseismic peak is available there. It's a nice strong signal. So we effectively took the coherence between surface and borehole, north, south, east, west component, and orientated the surface instrument until we had coherence of close to 1. And that was how we did that. And that's very easy now. In fact, I think there are so many software packages which does it easily for you, including Screen, which is what we use from Guralt.
Is there any other question from the floor?
What's the error? Small. Well, the error probably could be less than 1 degree. Depends how. I think it all depends on the signal-to-noise ratio and the number of averages you take But as you take more and more averages, and if you use north-south and east-west in such a way that, let's say you're looking at north-south to correlate, you want to get a maximum of one coherence, you can then look at north-south to try and get minimum. By averaging between the two, you can possibly go down to certainly less than a half a degree. I would say maybe close to about 0.2 or so. It's very difficult, of course, to really verify this other than looking at seismic signals.
Yes, Nurjan, please.
His innovative instruments made for Marsite projects. We were working together during this installation. Also, this instrument is the first time in the world, the dilatometer and others is just under the test bed. It's the calibration side, it's testing side. And the first time with the dilatometer and the three-component very broadband seismometer is just checking each other. And this is the very important calibration course practice of in the seismological world.
Yeah.
Thank you, Johnson, again for your contribution to the Marsite.
Yeah, thank you. Well, there has been other installations of dilatometers with short period 1 second instruments. But dilatometer being a long period instrument, you need really a long period instrument to calibrate it. And I think in this case, because one can see the earth tides from both dilatometer and the very broadband sensor, it then becomes reasonable to consider that you can actually calibrate it. Yes, and you can calibrate continuously.
Thank you very much.
Yeah.
Thank you.
The next presentation will be done by Mr. Topin. Its title is SPALAX New Generation, Deployment, Operation and Performances.
Thank you. Let's talk about noble gas now. First, I would like to thank the scientific committee and the CTBT organization to give us the opportunity to present the SPALAX New Generation deployment. My presentation will go through context and challenges. I will talk about the research and development period. Then we will focus about the design of the system, and I will finish with the roadmap for the next few years. So about the context, I think lots part of you have already seen this kind of slide. Here is a view of the current SPALAX system with the classical 3 steps. The first step is the air sampling and purification across membranes and compressor. The purification steps with the xenon separation and concentration across adsorbent materials. And finally, the detection steps with the detection of the relevant radioactive xenon isotopes. And I would like to say that roughly for the new generation of the SPALAX system, we will keep the principle of these steps for the next generation. And if I talk a little bit about the history and the key dates, 99 was a key date because it was the year of the patent. The first version of the industrial was developed in 2001 and 2002 at the period of the Fribourg intercomparison, double gas intercomparison. And 2009 was also an important date because it's the development of the shelter version, mobile version of the SPALAX. And if I look inside the international monitoring system, among the 40 noble gas stations to be installed on the IMS system, 13 SPALAX has been already installed or will be installed soon. And that includes 10 certified stations, plus we can also talk about several non-IMS systems for Canada, for France, or for CTBTO. So this slide is important for me because I will show you the main challenges for the new generation of system and what the aims for why we developed the new system. And the first one was probably to have a high sensitivity for the metastable xenon isotopes. At the origin of the treaty, maybe we didn't have a good knowledge of the atmospheric xenon background, and the detection of the metastable isotope at this time was maybe not so important, while now it's really important, and we know perfectly well that to discriminate the sources from a civilian or military event, the metastable isotopes play really a key role. The other point for us is to keep a high-resolute detector, high-resolute spectrometer, to have a quite simple analysis with low interference and low correction, and relatively clear signal to treat for the data center. Another point for us is to obtain a good source localization and high detectability. And for us, it go with the high sampling frequency, with a higher sampling frequency. And that is illustrated with this graphic. If you see here, at a given detection limit, we increase a lot the detectability of an event when going from a 24-hour sampling period to 8-hour sampling period, and 8 hours will be the target for the next generation of SPALAX. And last but not the least, it's much less scientific than the previous one, but it's really important for us to have, of course, high reliability and easy operation and maintenance, especially in harsh environmental conditions. And of course, we have a huge feedback on such experience, on experience of the current SPALAX operation with more than 15 years experience. And of course, it is taken into account for the development of the new generation of SPALAX. So I'm going now to the research and development part. The first part is the sampling stage. So for the sampling stage, the aim of the development was to increase the flow rate. And it was also to increase the enrichment across nitrogen membranes by keeping the power consumption as low as possible, because it's a key parameters. And so for the new generation, we are going from one spiral pump compressor to 2 piston pump compressor operating in parallel. And we're going from 2 air liquid nitrogen membranes to a new kind of nitrogen membranes that allow to enrich 2 times more the xenon at the end of the membranes. And so both evolution lead to xenon volume larger by more than a factor 4 compared to the current system. We improve, especially thanks to the compressors, the MTBF, by more than 30%. And we also have some redundancy because the 2 compressors will operate in parallel. But the purification and concentration development, this is an important work at CA from several years. We work on the development of new kind of adsorbent to make the xenon retention as efficient as possible. And here you have the xenon retention capacity for 2 different materials, the classical activated carbon and the materials developed at CA, silver doped zeolite, AgZSM5. And you can see that we have a huge gap in terms of xenon retention capacity between both materials. Indeed, we have a 15 times larger retention capacity. It leads to size and cost reduction, because if you look at the old design, we remove several parts of the old design to make the system much more simple for the new generation of system. All the data has been recently published in the literature. And the last part is probably the main important for the development of the SPALAX is detection development. So here is the shape of the current detector with a classical germanium high-resolution gamma spectrometer with the aluminum gas cell onto the detector. And if we look at the detection of a sample with metastable isotope with this detector by direct gamma detection, we have a quite bad MDC because the gamma emission efficiency for the metastable isotopes 131 and 133 is quite low. So the new generation of detector going to high resolution electron photon spectrometer with a gas cell with two faces of silicon pin that enable to detect electron, and we keep the high resolution gamma spectrometer, the germanium detector, and that allow to make coincidence detection about conversion electron and photon emitted by the sample. And as you can see, for the same sample, we have a clear signal in such a case, and we have a quite good MDC, close to 0.3 millibecquerel per cubic meter. So I come now more on the design, and I would like to tell that the design has been made with our industrial partner, Cegelec Défense. It was really important for us to have new shape of system to improve the operation, to make the operation and maintenance as easier as possible, and to improve also the way to install the system. So the philosophy is to put the system into 5 boxes, closed boxes when operating here, and the overall is 3 cubic meter for 1.5 ton and about 8 kilowatt for power. If I open the door now, in detail, the first module is a graphical user interface and power supply module. The second module is a sampling module that including the 2 compressors. The third module is a purification module that includes the membranes. The fourth module is a concentration with adsorbent and the archiving module to archive the sample. And the last module is a detection module. And you can see here on the top of the detector, the lead shield, a cosmic vetohead to remove cosmic emission for the detection. And you have also here the electronic acquisition system linked with the detection. About the operation now, as I mentioned, a key point is to have easy operation, and so it has been done by putting every part of the system into different subunits. It is divided in different subunits that are located on rail and that are fully removable. So it's quite simple to maintain the system thanks to this system. Another point, we have only few quick gas and electric connectors between each module, so it's also very easy, very fast. Only one connector for gas and one connector for electricity between the different modules. And that leads to have an easy installation, to have something very modular and very plug-and-play system with no heavy materials required to install it. And we have already tested that. It's really fast to install the system. It takes less than 2 hours, so it's very good for us. If I look about the GUI of the system, here is a general view of the process. You've got here the cycle duration. You can choose between 3 different cycle duration, 4 hours, 8 hours, 12 hours. Here you've got the level of the operator, expert of operator level. You've got here the possibility to have a remote access, remote driving of the system. You have here access to the spectrometer application designed by CEA to manage the new detection system. Here is the panel view with all the relevant information on the different view. Here is the general operating mode. You can choose, you can start and stop the cycle here very easily. There is lots of animation onto the GUI that enable to have a real-time status, real-time view of the system. And we have also more than 30 sensors that give a complete set of state of health data and that give the quality and that valid the data quality of the sample processed. Finally, we have also a direct alarm display and a quick view on the cycle progression. I will talk now more in detail also in the sequence of operations of the new generation of Spalax. So before to start the sampling, there is always a period of flushing of the system of about 1.5 hours. Then we start to sampling. The first 8 hours is for the sampling one, and the next 8 hours for the sampling 2. And during the sampling 2 operations, the first 1 hour and 20 minutes. It's used to make the quality control of the spectrometer. We use a QC system here that has developed to push sources onto the detector. There is a sample transfer and the system flushing. Then we have a 6 hour and 30 minutes of sample acquisition. And finally, we release a full spectra that we send to data center, and we archive the sample. And again, we make the same for the 8 next hour. If I look at the performance, and if I compare the performance of the SPALAX new generation to the previous version, about the power, we have a small increase of about 30% of the power consumption for the new system, but it's because we have to produce more xenon volume for the new generation of systems. Actually, by reducing the time of sampling by 8 hours, we increase the xenon volume nevertheless by about a factor 1.5. And so that means we increase the xenon volume by about factor 4, while we only increase the power by 30%. So for the spectrometer, I already mentioned that we use a high-resolution electron photon coincidence, and that leads to have a huge improvement of the MDC for metastable isotopes. And regarding the 133 and 135, we obtain almost the same detection limit, almost the same MDC for the SPALAX new generation as for the SPALAX, while we operate in 8 hours. So that was also a huge challenge, and that is given directly by the huge increase of xenon volume. About the roadmap to finish, so we signed a contract with CGLEC Défense at the end of 2015 for the design and the construction of the industrial prototype of the SPALAX. We almost finished the design and construction of the industrial prototype. It will be delivered at CEA in few days to a few weeks. And we will start a period of test at CEA. During those, we will start to send data to the PTS. And at the end of this period, probably beginning of 2018, CGLEC Défense will be able to start the commercialization of the system. And following this period, in collaboration with PTS and with Health Canada, because this on-site test will be done at Health Canada, we will perform on 6 months period on-site test to definitely validate the system. So at the end, for 1 year of data availability higher than 95%, we validate the system, and the system will be available for implementation on the IMS networks. So before to finish, I would like to thank the CEA team who works a lot on this subject. I would like to thank also our colleagues from Health Canada, because we have a very fruitful collaboration to come to this kind of results. Very fruitful exchange also with PTS, especially engineering and development section and IDC division. And finally, I would like also to thank our industrial partner, CGLEC Défense, and you for your attention. Thank you.
So we have time for 1 or 2 questions. Yes, please.
How about the memory effect?
So we check that, and it's much less than 0.5%. So for us, no problem with the memory effect, because we are clearly under 1%, which is the limit required for the certification, especially.
Another question. What kind of detect be used to detect the X-ray and the battery?
Didn't get it.
As you said, you measured the gas with coincidence spectra.
Yeah.
So you have a detector to detect the X-ray and battery.
Okay. Yeah. And so for the electron or beta ray, the detector is a silicon pin, the 2 face on the top of the gas cell. And for the photon and X-ray emission, the detector is the germanium classical BG.
Your detector to detect the X-ray and battery is a volume is hollow, and you add gas inside the detector.
You mean the gas cell?
Yeah.
The gas cell is about 13.5 cubic centimeter.
Okay.
The volume. Yeah.
Okay, thank you.
Okay, quickly, one question.
Thank you for interesting presentation. I have one question. What efficiency of xenon extraction?
Actually, the xenon extraction didn't well known to date. It's about 30%, but actually we are used to refer the xenon production compared to the electricity, the power consumption. For us, the important ratio is not the yield, the overall yield of the system. For us, the important parameters is the capacity to produce a sample of volume of xenon compared to the energy consumption, the power consumption. And for that, we are perfectly well. We are much better than for the current SPALAC system. Thank you.
Thank you. I'm sorry, we have to move to the next presentation. I have been asked to ask the person standing at the back to please sit in front, because we need to leave some space for emergency situations. So if there is still some space in front, so please come and sit. And then, yeah.
Okay, and the next presentation will be on the Sauna 3 project by Mr. Ringdon is presenting that.
Thank you very much. So this is a report of a project that we launched a couple of years ago. So the last SnT, 2015, I was standing here and presented the plans we had, and now I'm really happy to present the results. So this is the group working with noble gas detection at FOI. So I will start, before I go into the system description of the Sauna 3 system, I will discuss a little bit of the project goals we had and some guidelines we set up when we started this work. And then I will also show you data that we have been recording now since December last year, running a Sauna 3 and a Sauna 2 in parallel in Stockholm. So, we have been doing this in Sweden for many, many decades now. In the 90s, we had a manual xenon system and using germanium detectors, sampling for 5 days or so. Then we built the first prototype of the Sauna system in the end of the 90s. And then we had the Sauna 2, and then what's next? So we had to think a little bit which way to go. So what we decided was that we should not develop a completely new system, but instead do a major upgrade. And we would like to aim for considerably improved time resolution and increased measurement precision, and also address the user friendliness and reliability. And another thing that's really important for us is also to improve the data quality by addressing the energy drift and calibration procedures. We have had some drifts of the energy scale due to temperature, and we wanted to address that as well. And also improve the calibration. So we set up a couple of requirements for this system. And the first one was that it should be an upgrade of the Sauna 2 system. We should be able to keep the same footprint and power consumption. And we should also keep the sauna concept, which we say is operation at ambient temperature. We don't have cooling in the system. We increased the time resolution to 6 hours instead of 12. And also 4-fold increase in the sampling capacity. We will go from helium to nitrogen as a carrier gas, and develop an automatic adjustment of the detector energy drift. And another thing we have done is to introduce also a stable xenon measurement before and after the cell as an extra QA/QC control. And then finally, simplify the operator software as well. So looking at the different components in the system, the ones in yellow here are the ones that you replace now if you upgrade from a SONA 2 to a SONA 3. The first sampling rack, and then also the process oven, the GC, and software, and also the beta cells. And this is a project timeline that we used, and we have now delivered the production documentation to our commercial partner, SnT Sensor Systems, and they are now producing the first commercial prototype. And I think it should be ready then for production for sale in 2018. So now let's look at the system a little bit more closely. So these are the main components. And we have a pump, which is now also piston pump, as we heard from the previous speaker as well, with a 4-fold capacity in airflow at least. We have introduced a new component, which is the pressure swing absorption unit, and that is a really important improvement of this system. Then downstream of that, we still have the same configuration with 2 sampling ovens in parallel, a process oven, a gas chromatograph, and a detector and archive. Like that. So the gas process is now 6-hour time resolution. We produce more than 3 milliliters of xenon per sample per 6 hours. The airflow is 120 standard liters per minute flow at 7.5 bar. A nitrogen as carrier gas. And also the processing is faster. We have in SONA 2 we process the sample in 7 hours, and here instead we can process it in 5 hours roughly. And we also use silver zeolites, and we get then smaller traps and lower power consumption as well. So the PSA looks like this. It's a 2-stage PSA. The first step removes carbon dioxide and water, and the second step enriches in the air in xenon, around a factor of 10, going downstream then into the rest of the system. And we are using molecular sieves for that. Yeah, it's not working here. The sampling ovens have changed a lot since we're now using silver zeolites instead. So in the SONA 2 we had 4 kilograms of charcoal in each oven. Now we have only a couple of 100 grams of silver zeolite instead, and you can see the difference in the size of the traps in the ovens. And we can also then make the ovens much smaller. So we based the new ovens construction on the OSI system design. And you can see a picture here that's from SnT manufacturing the first commercial sampling oven here. So this is results from what we have got since November last year. But the system has been running since August last year with respect to the gas process. And it has been producing very steadily more than 3 cc of xenon per 6 hours. And you can see a slight decrease over time here, and which we believe probably is due to the pump that at some point needs some service. We haven't done that yet. So, but I think this result looks really promising. You can also see here we have 2 dots. The brown ones are the ones measuring the xenon volume going into the system, and the blue ones after the measurement in the detector cell. Then we had some period where we had a leak in valve. I marked that with this blue rectangle there. Then let's go to the detector. We decided to keep the old sodium iodide crystal that's in the system. But now we have nitrogen as a carrier gas. That means that we will have more straggling in the sample. We have larger atoms compared to helium. So we had to redesign the detector cell to be able to keep the energy resolution of the beta. We did a lot of simulations using Geheime, for instance, and we have refined the polishing and coating techniques to reduce the memory effect, which is now 0.06% in the cell. So that's really very small now. We have tested different sizes of the cylinders, and we ended up with one which is 18 cc compared to the old SONA 2 cylinder, which is 7 cc. And we have a 100 nanometer aluminum dioxide coating to reduce the memory effect. We have new detector support and new PM tubes as well. And this has resulted in a resolution with much more xenon in the cell, 3 milliliter compared to 1.5 before, and also nitrogen instead of helium, but still we could keep and even lower the energy resolution. So we have now achieved, for several cells, 29 kV at 130 kV energy, which is, I would say, pretty good. And the efficiencies you can see here, I compare with the Sauna 2 in Stockholm, and you can see that they have also increased a little bit, actually. So we have kept the energy resolution, and we have kept and even increased the efficiency a little bit. The energy drift reduction using automatic adjustment of the gain of the different PM tubes. That's done by comparing with a QC, master QC spectrum. And we are fitting the entire spectrum, not the peak fitting, but the entire spectrum using maximum likelihood fitting. And that works very well. So now the gain stability is better than 1%. For the sodium iodide, it's even lower than that, but for the beta, it's around 1%. You can see here what happens when we have the correction on, and then we shut it off, and we even provoked a little bit of drift using a desk, office desk lamp to heat it up, and so on. You can see the drift. And then when we turn on the correction again, you get a stable energy scale. We have new operator software. I won't go into detail on that one, but the main point is that we have one GUI for everything now in the system, instead of several GUIs before. So now let me just finish by presenting some data that we have collected. We're running one system one IMS system at the roof at FOI. This is SCX63. Then we have the Sauna 3 system running at another building, having an air inlet closer to the ground, like I show in the picture here. To illustrate how better the improvement in data, I show here two spectra. One from the Sauna 2, which is above, 11-hour counting time, and the other one is 5-hour counting time with the Sauna 3, and the same activity concentration in both samples. So you can see the improvement in statistics between the Sauna 2 and the Sauna 3 with the same amount of radioxenon in the detector. That's just an illustration of that. The sensitivity looks like this. This is the MDCs that we got, average MDCs we have after half a year of running into comparing the different systems. And you can see we end up with around 0.17 and 0.15 millibecquerel per cubic meter for the metastables, and 0.2 and 0.3 for 133 and 135. And you can have a look in more detail in a poster outside if you want to look at this data in detail. The activity concentrations match fantastically well between the two systems. So I think this also gives confidence that this is really working. It might be a little bit hard to see on these pictures, but you can see the impact of having 6-hour instead of 12-hour time resolution. You can see to the right, you can see how the peaks, the plumes are revealed. You can see that a broad plume with the Sauna 2 system now shows up to be a double plume with the Sauna 3 system, for instance. And that, of course, will give you a much better atmospheric transport performance and location capabilities. We had quite a lot of multi-isotope hits during this test period because of a nearby power plant that has been having some problems with fuel damage. So we get 3 and even 4 isotope hits quite often. This resulted in these 3 isotope plots, for instance. And I think this is the absolutely best illustration of how we now have increased the verification capability of these systems. The one on the top is collected by the Sauna 2 system, and on the bottom, the Sauna 3 system. Measuring on the same air, we get this very much improved response in this multi-isotope plots, which is one of the most important tools we have for source identification and source characterization. You can see we go from 9 samples to 31, measuring on the same air, and the error bars are also smaller. Remember, there's a log scale in both X and Y. To sum up, the Sauna 3 prototype performs according to expectations. The xenon production is stable. We see no sign of degradation of adsorbents. The detector energy and efficiency improved, and the drift is below 1%. We have new software, and I think this comparison experiment showed that the verification capability has increased substantially. The first commercial unit is under production. Thank you very much.
So we have time for question. Yes, please.
Thank you. Great talk. So you had 2 detectors in the picture. Are you counting for only 6 hours?
Yes, we are. So we still only have 2 detectors, given, but we have twice the sampling frequency. So that's. But you can, of course, think of doubling that amount. But the plan is right now to use only 2. But
Okay. I would love to see us count for the Xenon 133M for half of a half-life. I'd love to see the systems be able to do that for 24 hours, which means 8 detectors, I think. Is a lot.
Would be nice, yes.
Any other question from the floor, please?
Okay.
Thank you. So after this 2 presentation on new generation of noble gas system, we'll move to a presentation more related to on-site inspection technologies. And
The next presentation will be done by Mr. Saul, and which title is SCO TSS Gamma Imager for CTBT on-site inspection.
Thank you, and thanks for giving me the opportunity to talk here today. For those of you who saw Steve Creek's talk yesterday afternoon, this is basically the same talk. It's just a different Compton Gamma imager that I'm showing. His talk was based on an imager that uses high-purity germanium, and this one is based on scintillation, and is much bigger and therefore is much more sensitive. So there are many people involved in this. I won't go through them all. Actually, I won't go through any of them. So the outline of my talk is like this. So first of all, I'll motivate why one might use imagers for on-site inspections for CTBT. I'll go through what Compton Gamma imaging is, or the method is. Introduce mission-ready project, imager project we have for building imagers for safety and security. And then go through a study of a scenario that was played out at the integrated field exercise in 2014 in Jordan, and basically try to answer the question, how could an imager have helped at that point? So it sounds very much like Steve Creek's talk right up to now. But I will be adding real experimental data in. So why an imager? So cutting right to it, this is the scenario that we would want to investigate, a no access zone. You can't get in there, you're barred from flying over it or walking it or driving it or what have you. But if you had an imager to look in there, you'd be able to see what was there. So with direction blind instruments, you need to do a survey and map out and find intensity spots and do some time expensive post-processing often. But in this case, you wouldn't be able to do it because you couldn't access the region, and an imager would help you. And this situation actually did occur at the integrated field exercise. This is stolen from a talk. Here is shown a region that the inspectors were not allowed to access, but they could walk around. And here they are looking down from a ridge into an area that they weren't allowed to access, probably wondering or wishing they had a Compton Gamma imager. So this is the question we want to ask. If they had a Compton Gamma imager, what would they have been able to do? Would it have improved things? So what is the Compton imaging method? There are there are a few methods for imaging gamma rays, but we are using Compton Gamma imaging. So essentially, you have a detector that's split into 2, a scatter and absorber part, and you hope that your gamma rays come in and scatter, Compton scatter, off an atomic electron in the scatter part, and then carry on and fully absorb in the absorber. And if you reconstruct the total energy of that gamma and the energies of the individual hits and their positions, then you can reconstruct up to a cone of opening angle given by the energies here the direction from which the gamma must have originally come, with cone axis along the axis of the two hits here. So that's for a single event interacting in your detector, a golden event, if you will. If you have multiple golden events, then of course you can to overlap them and get the direction to your source. This is for a point source. Extended source is a little bit more involved, obviously. So here's what this cone does for you. So this is a simple back projection, horizontal and vertical field of view, so horizontal and vertical. And the cones are back projected as circles onto that, and here after a few seconds of a detector, which I'll showcase later, you can see that there's a hot spot building up, and after several minutes you can see a clear peak with a clear indication of where the source is, and so you can already see what this is going to do for an on-site inspection. We've been building Compton, or working with Compton gamma imaging for 10 years or so. We've had a few milestones. So in 2012, we completed 2 benchtop R&D gamma imagers, fairly large volume. One of those I'll showcase later. And last year, we fielded or built and fielded a small handheld Compton gamma imager, and I'll showcase that one as well. We are currently working on commercializing these imagers, and next year they will be available for order. And that's called a mission-ready project. Here's what the mission-ready project looks like. It's a modularized design for Compton imagers. So in its simplest form, it's just 2 layers, 4 by 4 in each of the scatter and absorber. These are cesium iodide crystals read out with silicon folded multipliers, very compact, very light. And here's a 3 by 3 version, much bigger. So we'd like to see, what if we had these things, or one of them or both of them at the site, what would they have done for us? As I said, this design is modular, so it targets different price points and mission spaces. And we have a lot of end users on the project, so this will ensure that what we get out the back end is actually going to be useful. And an experienced industry partner, Radiation Solutions, Inc., which have a lot of experience fielding rugged instruments, mapping, automatic gain stabilization, compact electronics, etc. We don't have these imagers yet. That's what they look like. I'm not going to go into the details. As I said, it's going to be next year. But I want to point out that the total volume of the 3 by 3 is nearly the size of a sodium iodide log, a 4-liter log. So this is a very sensitive instrument. It not only does imaging for you, it also does surveying mode for you. So it's a dual-use instrument. You can drive around with it, so do surveys, and then stop and image. So we use 2 proxies here in lieu of the single module and the 3 by 3 array imagers. This is the single module fieldable imager I said we fielded last year. We call it the Jiffy, the Joyful Interim Fieldable Imager. Here it is in the field imaging 370 megabecquerel cesium-137 source. It's in the van here. There's the source. This is RSI's RAD Assist software. Here's the breadcrumb map showing the intensity of this higher intensity here, spectrum, cesium-137, etc. This is, as you can see, a sensitive spectrometer, which also allows you to do imaging. So here's the imaging of the same source. We're at 40 meters, and in 62 seconds, with the simple back projection model, you can see a little bit of overlapped intensity, but we also have a point source algorithm that allows us to reconstruct the position of the point source, and there we've nailed it down there in, as I said, 1 minute at 40 meters. There's the spectrum. In order to characterize our imagers, we use something called time to image. Well, I'll get to that after I get to the proxy for the 3 by 3. This was built in 2012. The front part is the scatter and is cesium iodide read out with a silicon photomultiplier. The rear of the absorber is sodium iodide read out with conventional PMTs. But to characterize how well this thing works, we construct something called time to image. This is the angular precision with which we are able to reconstruct a source in space as a function of the data acquisition time. And this is experimental data. We just chop the data up into multiple sets of the same amounts of time and keep reconstructing the position of the source over and over again, and we determine how well clustered those things are. So what this is telling you is that we were able, in less than a minute, to reconstruct a 22 megabecquerel cesium-137 source at 10 meters, its position to within 1 degree precision. And to give you an idea, the dose rate from that source at the detector is the same as background. So this is pretty good. This is what it looks like in the lab after 4 seconds of data taking. Same source. This is the 1, 2, and 3 sigma probability contours for the location. It's actually up there. And this is what it is in 60 seconds. And we can do multiple sources at the same time just by windowing on their energies. Okay, finally, I hope I haven't run out of too much time here. This is the study on the integrated field exercise. This is the area that, site N, that we were unable to access. So they were up here on the ridge, staring down longingly into this section here, where there were buried 10 40 megabecquerel cobalt-60 sources, 400 megabecquerel total at depths of 10 to 50 centimeters. And this was supposed to be a proxy for iodine-131. So we simulated what we might have expected here with a 3x3 array imager. And we also imaged that a cobalt-60 source of equivalent dose rate in our lab with the two imagers that I've showcased already. So there's some assumptions. The imagers have been deployed from 60 meters from the source area, and it's a point source, which was not the case. They were distributed a bit, but from a distance it would look point sources. So these are the results for the Monte Carlo simulation done with two packages, and they agreed. Here's the cobalt in black, time to image, so 1 degree resolution, able to localize that source in 20 seconds. Iodine-131, which is the thing it was supposed to be a proxy for, is up here, and you can see it takes a little longer to image, but if you were to stick with 2 degrees, you can see that we can reconstruct the source position to within 2 degrees precision in under a minute for iodine-131, cobalt-60, and also another OSI isotope of interest, zirconium-95. Now, these simulations were done without any norm background, unlike Steve's talk yesterday, and no Earth was simulated, but air attenuation was taken into account. For other OSI-relevant isotopes, what we've done is gone and calculated the times to image for the ones in blue here for this list, and you can see if you just stick down on the 2 degree precision, if that's what you want, we're talking tens, maybe a few minutes in order to localize the source. This was stolen from there. In interest of time, I'll skip that, but come back to it if anybody has any questions. Okay, so that's Monte Carlo simulation. We can also do this with real experimental data. So we found a 22 megabecquerel cobalt-60 source and put it at 15 meters in our lab. That corresponds to 400 megabecquerels at 60 meters. And we buried it in, well, either bare in front of the bucket or in different layers of distances from the front face back, 10, 20, 30, and 40 centimeters, to mimic what it would be like if it were underground. This is the view from the imager itself. And we image those things with both of our imagers. This is the setup. Imager in one end of the room. There's our bucket. This is bare, 10, 20, 30, and 40. Well, you can't figure that out from my shaking hand, but anyway, there you go. 15 meters. And we're in a concrete, a floor in the basement with concrete walls. There's a lot of background. So here's the image with the bare source, 20 seconds of integration time. Here's the spectrum. Overlaid in red is the norm, is the background without any sources in the room. There are cobalt-60 photo peaks. And here in 20 seconds, we were able to reconstruct the position of the source. Here in 1 minute's time, same spectrum, we were able to get the precision a bit better. That's for a bare source. Here's 10 centimeters of sand for 1 minute. We see we've reduced our peaks, but we're still able to reconstruct the position of the source. 20 centimeters of sand in 2 minutes. We can hardly see those photo peaks, but if we go with the log scale, you can see they're still there, and we can reconstruct the source. 30 centimeters of sand. Okay, we're struggling now with the simple back projection, but our algorithm does locate the source, and our peaks are pretty much gone, such that if we go to 40 centimeters, I don't have anything to show you. I couldn't do it. We couldn't do it, sorry. Okay, this is the summary plot for that. Cobalt-60 bare, cobalt-60 20 meters of sand. These are the times to image. Again, cobalt-60 source position reconstructs to within 2 degrees in under 1 minute. And I won't go through the details with the Jiffy, because it didn't perform that well, or didn't perform as well, and I don't have the time. But here's a bare source, 120 seconds, and you can see we're able to reconstruct the position. There are photo peaks. And this is sort of a summary slide for everything, for the 3x3 and for the single module imager. And I remind you, the single module imager is integrated with RSI's RAD Assist, so there's alarming available. 3x3 array. I kind of lied here. Either change this to 2 minutes or put an X there. But anyway, we were able to, within 2 degrees, in less than a minute, reconstruct bare 10 centimeters and 20 centimeters the position for the 3x3. And for the single module, which is probably more likely what they would have had on that ridge, they would have been able to do a bare source and something buried in 10 centimeters of sand in under 10 minutes to 2 degrees precision. And that's just holding your thumb up on the ridge and looking down like that. And that's where you would have to go from there. In all cases, the single module imager alarmed on total counts. And so it's functioning as a survey instrument. And if you just windowed on the Cobalt 60 peaks, it alarmed up to 20 centimeters of depth, but not on the last two. So in summary, we think the gamma imagers are ideal. Well, they are ideal for seeing into areas that you can't access. And for areas like, let's say, Fukushima or something, you don't want to be around for very long. Put it up in the air, turn it down, and image the view, get out of there. We're developing a large volume modular system, Compton gamma imaging system, that doubles as a sensitive spectrometer and an imager. Radiation Solutions, actually CTBTO already has their instrumentation, and this instrument will be sort of a drop-in replacement for the direction blind logs. So you don't really have to do much in order to get this system up and working. And we've successfully tested this in the field, and the commercial versions will be available next year. Thank you.
Thank you. Is there a question from the floor? Okay, okay, sorry, please, Nick.
In the OSI type of environment, the environment is going to be dirty because
Yes.
in Homeland Security or proliferation type of thing, you have a point source. Can you comment about
How they would be, how to
Yeah,
perform in
how it's-
multi-gamma environments?
how it's going to be when there's other stuff spread out and then localized?
Yes. So the simulations that we showed were all done with the real sources. They weren't just the lines that the energies, or the dominant energies, if you will. So there are many of those sources that were reconstructed with all of their gamma rays present, and that can potentially confuse your reconstruction algorithm. That doesn't answer your question, but it does tell you that in an environment where you do have a lot of other crap around there, we can still do it. These are all point sources, so I admit that if you have it spread around, these numbers don't apply. That'll take a longer amount of time, but you do have the algorithms available to you to do that. So until we try it, I cannot answer your question, but it's not, I would not say it's definitely not a showstopper. It just will take a little longer.
Thank you for your presentation. I got a pretty simple question. How does Compton imaging compare to simple collimation for, if you just don't need to image it, if you just kind of need to know that that direction there's a radioactive source,
There's a lot
as
less
far as
lead.
count times, et cetera?
There's a lot less lead. So that would be passive collimation. This is often termed active collimation. You don't have to carry around all that extra lead in order to do the collimation, right? So that's the first thing. And the second thing is, in order to do higher energies, you need a lot thicker lead. Oh, I'm sorry. In order to do collimation at higher energies, you need to make your lead pretty thick. Otherwise, you get punched through. So what you're asking works in certain instances, and if you're not going to be carrying it around, and you don't want your first responders to be lugging it around, then it's fine. It's not necessarily very fast, but it's very heavy, the collimation.
Do you have like a rule of thumb as far as a count time or a sensitivity limit, or so we can?
So that allows me to go a little further and say, in some sense, those methods are complementary. I wouldn't use so much collimation as I would use something like coated aperture or self-shielding. So at the lower energies, Compton gamma imaging, it's the slide I skipped over, can't do it because one, you don't have this Compton scatter cross-section, and two, well, it has to do with triggering, but you can't do it. So you would have to move to either coated aperture or pinhole or shadowing. Yeah. And collimation would also work well there.
Okay, very quickly, last question. Okay.
Hello?
Yeah, at the back, sorry. No, there is a question at the back.
Yeah. Is there any reason that a human being has to be involved in using this equipment, making a measurement, or could it be mounted onto a remotely operated or autonomous vehicle?
Well, I know that there are instruments already mounted out on UAVs. It is certainly something that we plan to do. We have a similar instrument that uses 8 crystals, doesn't use Compton gamma imaging, but uses shadow effect, that does something like that. But no, we will have different modes for this thing. One, an expert mode where you would have a lot of interaction with the user, but another one, just sort of a single button push, and you just, whatever it is you alarm on, you automatically go through and try to image. So no, you don't need somebody involved. It can be done remotely, no problem.
Thank you.
Okay, last question very quickly, please.
Yeah, could you say something about your experience with the silicon pin photomultiplier tubes? Great, terrible?
So you just make the same mistake that I always make by putting tube in there. It's it's not a tube, yeah, but I always do that. They're wonderful. The first version that we had, was that I showed you on the screen there. That was made for our prototype, and they were very noisy, and they forgot to put the protective coating on them, so as a function of time, these things have started dying and getting worse on us. But the latest batch that we've got has fantastic energy resolution, very low noise. They perform as well, if not better, than the PMTs that we have in the rear. The cost is coming down markedly, and if you're not using SPMs, you should be, unless you're doing something that requires very low noise.
Thank you very much.
Thank you.
Okay. In our last presentation, Mr. Florido will be presenting a new gamma viewfinder concept.
Thank you, Chairman. And thank you to my previous colleague, because I will follow in the same subject, and I will use a little bit of their examples. Present gamma cameras are based in different ways in order to produce the picture. There are several cameras available in the market. One of those cameras have several types of collimation techniques. One type of collimation techniques are pinhole cameras. Other cameras are coded aperture cameras. Other are narrow collimators or shadow effect cameras. And also there are Compton effect cameras available on the market. These are a divergent, in the lower you could see a divergent narrow collimator, another in a pinhole, another this is a Compton coded aperture, and this is an available Compton camera. When you look for real picture, for example, in Fukushima, the first one is a really garden in Fukushima. And you could see this has been taken with a coded aperture camera, picture taken in Fukushima with a Compton, a coded aperture camera in a garden in Fukushima. Another is in a waste treatment plant. Another are 2 examples inside a van. And the last one is in a laboratory. Real pictures taken with different cameras. We are proposing an additional way in order to produce a picture. It's a modification of a shadow camera. The idea is to use not to try to use 2 detectors and look for a coincidence. It's not a Compton type of camera, and we are not trying to use a collimator. Basically, we are trying to use we call it lobular view. The idea is to produce a picture in real time. Our dream in the future is to try to have a gamma film. One way to see how you could produce a lobular view is, instead of to think in our eyes, our type of eyes usually are called complex eyes. There is another type of eye, the ant eye. The ant eye is a composed eye. In the composed eye, like the ant, you basically, each eye looks in a lobular view. And doing the correct math, you could try to calculate what is the crosstalk between the different eyes, element of the eyes. And also, you could develop not only a full 2D eye, you could try to produce a 1D eye. And one element if you're, in your eye could see or integrate all the photons at different elevations. And then we call it, is from my colleague, they call it tangerine detector. It's because each eye is looking like a tangerine slice, lobular. And then you could try to calculate and develop the math in order to see the different crosstalk between the different elements of a tangerine slice. We call it ant eye, the first one, and the second is we call it the tangerine detector. Initially, we started in this way in order to understand how could we use the crosstalk between the different detectors in order to deconvolute the position and the angular resolution of the different sources. By simulation, we use standard Monte Carlo calculator method like MCMP. We develop our own Monte Carlo tools in order to use the Monte Carlo tools in order to design the optimal combination of the different lobular views. And also, we develop analytical methods in order to understand what is the basic math behind the lobular view. Basically, to understand if you need to increase or decrease the couplings between two neighborhood detectors or lobules. And always using all these handmade analytical calculation and Monte Carlo, we develop some mathematical rules in order to design a lobular view type of detector. And then we evaluate if it's an attractive method to have an accuracy measurement of, for example, 1 degree or 2 degrees of angular resolution. And we develop some algorithm in order to reconstruct the position of the source. We think that the results looks attractive because we could reach 1 and 2 degrees of angular resolution theoretically in a short time. This is a typical Monte Carlo simulation of a picture taken in less than 1 second. But this is calculation. This is basically okay, doing math. But the reality do not need to fix your math. So in addition to we start to develop, we work in Argentina in a place called in Bariloche, and in Bariloche there is a big facility that they work with us. It is the reactor RA6 in Argentina. In this RA6 facility, we perform the first set of experiments, basically using a tangerine geometry, looking in lobular views, and we put Geiger detectors with some specific design, but using our Monte Carlo methods and the analytical methods, ways in order to design the crosstalk between the different detectors. We develop this, and each signal, you need to process the signal in real time in order to do all the math and inverse some calculations in order to give you the signature of the system. And then, if this could be done so fast, maybe we could move the source or move the detector and see on real time if the pattern is really moving or not. We did it, and basically, instead of move the source, we put the source fixed because inside a shielding cask, and we put the source fixed, and we move the detector. And we try to see in real time, when we move the detector, if we could see the source with a proposed resolution of about 1 or 2 degrees. We performed the test, and it is how they could see in real time to move in less than 5 seconds the position of the source in the lobular tangerine geometry. Doing some math, you could calculate what is the angular resolution doing this type of comparison. We are close to 1 to 2 degrees in 1 frame per second. For us, we are fully convinced after these experiments that the lobular view method to produce an image is a reasonable technique, need to be explored. We supported this with our math on Monte Carlo analytical models, and we supported with this first of experiments in the RA6 reactor. Then we will follow trying to produce a real-time imager without using collimators, non-coded aperture, no pinhole, not divergent or converging, or no shadow effect, and without using coincidence or two layers of detectors. Why? Because if you're using only one detector, your weight will be lower and the cost will be lower. So it's cheaper, or need to be cheaper, or if it works, will be cheaper, and could be run at relative higher velocity. Our dream, our holy grail is trying to achieve a gamma film. 10 frames per second could be a dream, but you need to follow in order to create your dreams. An advantage, if we could produce a 1 picture per second or 10 pictures per second, we could, in a compact and lightweight equipment, maybe you could do a transportable equipment that could be used in the field. And you could combine the lobular view with optical cameras. At the end, we think that the principles we proved experimentally, and theoretically the image could be obtained using this method, without photon rejection, or without photon rejection. We call it internally photon rejection, the collimator's rejection. In the collimators, you are producing the images losing photons, paradoxically. You are trying to produce the image rejecting photons. In the coincidence detector, like the Compton camera, you are basically using a clever use of the Compton scattering, but not losing photons. Right now, we are planning not to use more Geiger. We are using cesium iodide, and we start to build our camera using cesium iodide detectors and photodiodes. First, we target it as a practical use, a 1D tangerine geometry equipment to be used for surveillance, for example. And could be used also to support, as our colleague previously explained, to support on-site inspection. Imagine that using a UAV, you could use the UAV in order to correlate the position of the source with the image, the optical image, with the gamma image. One advantage of the lobular view is, maybe some of you are aware that there are some type of radars that are called synthetic aperture. Using the tangerine geometry, you could move the direction in direction of the in the central axis of the tangerine in order to scan and produce the second dimension of the picture doing some calculation of synthetic aperture. And you could deconvolute the central axis of the image in the tangerine detector using the math, using the property of the velocity and in which you are moving the cameras. You use this type of technology in radars, in synthetic aperture radars, in a satellite radar, for example. In the radar, you do a single. You have a single element of row, and you use the satellite movements in order to produce the second direction. You could use, if you put in a UAVs, this type of tangerine detector, you could use the direction of the flight of the UAVs in order to produce the second direction in your picture. Also, you could use the tangerine slice detector in order to, in real time, put in a checkpoint and look for example, orphan sources or illicit traffic of radioactive material. Thanks.
Thank you very much. So we have time for questions.
Okay. No, it's okay.
Please.
I'm just curious what the strength of your source was.
We use a very small and low efficiency small Geigers. But our source is 20 times higher than your source, 20 times. The efficiency of our detector is maybe less than 1% of your efficiency.
And what distance was the source?
We changed the distances. We changed from 2 meters to 5 meters.
Okay, so thank you very much. And now I think we'll move to the poster previews. So we have 18 poster previews registered. I hope all the presenters are here. And we'll start with poster 7.
Number 7. And number 7 is, the title is Adding Wireless Capability to an IMS Portable Infrasound Array.
Okay, so I guess the person is not here, so we'll move to the second one.
Which is number 9, automated testing of our RASA software development environment.
Hi, my name's Eddie Tillestrand. I'm an engineer at GDMS. We're the equipment provider for the RASA particulate system and the station operator for the U.S. radionuclide stations. This poster demonstrates the software testing environment we've created. We have a virtual environment where we can simulate any RASA hardware configuration. We currently support 4 different MCAs and a lot of different ancillary equipment, and we can simulate any of those virtually, test our software, and also we have some hardware test developments where we could test multiple our system instrumentation units or detectors without using resources we'd otherwise be using, and we can get software and hardware upgrades in the field faster. Thanks.
Thank you.
Thank you. Okay, the next is number 11, CLYC scintillator, a possible enhancement for handheld OSI detectors.
Yeah, good afternoon. I'm Charlotte Bornhöf from the Fraunhofer INT in Germany. We studied a detector equipped with a Glück crystal. It is able to detect neutron and gamma quants simultaneously while enabling discrimination by energy and by pulse shape. These characteristics would make a Glück detector a possible enhancement for future OSI detection devices. Thank you.
Thank you.
Thank you. Next one is Mr. Gomez is here. Okay, we'll go to the next one. It's number 13, cross-calibration of airborne and ground-based gamma radiation survey techniques under on-site inspection condition.
Good afternoon. My name is Xavier Blanchard. I'm working at the CTBT OSI division. So this is a teamwork, and I would like first to thank the various contributors, the Austrian National Authority for providing us access to their aircraft, military aircraft, and also the training site, which is the biggest site in Austria that has actually a flight calibration line, which is used by European emergency response teams. Also, Geological Survey Austria, who provided calibrated cement pads. We describe here the methodology to calibrate a wide range of OSI in situ systems, including field in situ measurements supported by laboratory analysis of samples. And the results inform several of our OSI action plan projects. It helps us improve our current capabilities and also provide modules for training advanced course, including improving our field exercises. So whether you are just curious or involved in the inspectorate training, or actually an expert in the fields who would like to support our efforts, please join P13 at 5 p.m. I'll be there in Festsaal.
Thank you.
Next one is number 18, Mr. Hayes, development of a field portable argon 37 monitoring capability.
Hi, my name's Jim Hayes. I'm from Pacific Northwest National Lab. And my poster is about development of an argon 37 system that can be taken out in the field and measure soil gas samples. Our goal is to be able to measure 6 samples, and we've demonstrated this in 24 hours. We have 7 nuclear detectors. Come see the poster to see what our MDC is. We've also made a lot of measurements around the northwest of the United States and seen argon 37, where we've also developed an algorithm to be able to predict how much argon-37 is in the soil. So come see how well our correlation is at the poster. Thanks.
Thank you.
Next presentation, number 19, development of the silicon pin diode detection unit for noble gas system ARIX. Nobody? Okay. Let's go to number 21, development of in IMS infrasound array geometry tools.
Good afternoon. My name is James Robertson with CTPTO IMS ED. And this poster that we've put together is about recent tools that we've developed over the last few years for designing infrasound array geometries. In the poster we describe how we came about the method to make this tool, how we've tested it, and a test setup that we actually did in a site survey at IS01 Bariloche in Argentina last summer. And all the results and the planning and some information about these tools are displayed in the poster, and I look forward to you stopping by at P21 this afternoon, 5 o'clock. James Robertson, thank you.
Thank you.
Next presentation is number 22, implementation of new technologies at the IMS radionuclide particulate station.
Good afternoon. I am Nadalut Barbara from the Engineering and Development section of the IMS at CTBTO. We are very much engaged in very close cooperation with system providers and software developers in evaluating the latest technological developments. In these posters, we describe the various ED projects and the solutions which are tailored to the specific needs of the CTBTO network. Thank you.
Thank you.
Next one is number 23, improving MDC at the radionuclide particulate array system.
Good afternoon. My name is Radha Hong. I work with General Dynamic Mission System, and my poster is about trying to improve the MDC within the RASA system. So there was several experiments that we run at our facility to try to improve the MDC, and one of the things that we find out that the best simple way of installing and try to be cost effective is pretty much the LED plug behind the CP5 plug. And we install two of the plug in two of our sites right now, and we show about 8% improvement in our system. Thank you very much.
Okay. Number 28, next generation novel gas system for the IMS network.
Hello everybody, my name is Romano Planteda from Engineering and Development section in the CTBT IMS. So in my poster I will walk you through the project which my team is engaged in, and especially on the noble gas, the modularity, the sustainability, and the availability, the effort that we are very much engaged with the producer, but also our R&D testing, and also the revival of the ING portal for sharing scientific information. So just come and we will talk about that. Thank you.
Thank you.
Number 29 is operational interface and capability of a carbon survey instrument developed for the PTS under USCAK.
Hi, my name is Stephen Creek from Lawrence Livermore Laboratory in the U.S. This is actually one of two posters, so you'll see me again in a minute. This is a project that had leveraged a system designed for the U.S. Department of Homeland Security about 10 years ago called the Adaptable Radiation Area Monitor. It's a very simple operating interface that operates, in this particular case, a carbon survey instrument, which we just delivered a couple of these to PTS within the last week or two. So come by. Thanks.
Thank you.
Number 32. Sensing ionospheric disturbance using a large GNSS network.
Hello, my name is Jim Garrison. I'm in the College of Engineering at Purdue University in the United States, and I'm going to be presenting a alternative phenomenology complementing seismic, infrasound, and hydroacoustic measurements, which makes use of the interaction between the neutral atmosphere and the ionosphere. And through observing perturbations in the ionosphere with electromagnetic methods, we have an alternate method of detecting disturbances. This is not new. The physics were studied in the 70s and 80s. However, at that time, practically active radars were not cost effective. What's happened since then is we now have global networks of very dense GNSS receivers for geodetic applications. We've developed some new array processing techniques in the wavelet domain that allow us to detect these coherent disturbances, estimate their speed and direction of propagation. So I'm poster P32.
Thank you.
Number 34.
Hi, I'm Gus Caffrey from Idaho National Laboratory. OSIRIS has been extensively tested over the past couple of years, and those tests included an unscheduled 1-meter drop test, operation amid legacy radionuclides at the former Nevada test site, hot and, as you can see in the photo, cold weather outdoor testing, a 1-year fission product source decay study, and the riskiest test of all, frequent operation by undergraduates. Come see how OSIRIS fared, see our poster. In addition, right outside the door, you can see the drop-tested OSIRIS spectrometer at the Ortec booth. Thank you.
Thank you.
Number 35, the calibration of IMS, seismic and hydroacoustic T-phase solution stations.
Hello, everyone. My name is Ria Otsuka. I've worked at CTBTO, the International Data Center Operations Section. I introduce this poster as a representative of the Waveform Technology Group of Operations Section. The poster is about the calibration of IMS seismic and hydroacoustic T-phase station. And the poster showed the background of the annual plan calibration and the method, and then result from calibration 2016. I'm looking forward to seeing you in poster 35. Thank you.
Number 37, the radiological field training simulator for radiation detection training without radiation source or in on-site inspection.
Hi, so I'm back again. So this is actually a follow-up to a 2015 SnT presentation that I had given regarding a training simulation concept that we were developing at that particular time. Since then, we've actually come up with a prototype and are working on a second prototype. What this does basically is allows an operator to use an operational radiation detection system, and this is a pulse generator, a GPS-capable, network-capable system that injects signals into the preamplifiers of the detectors, or excuse me, into the amplifiers of the detectors, so that an operator in the field can experience what it would be like to walk around in a high radioactive area or a contamination zone, and their instrumentation will operate just as it would if there were real radioactivity there, but without actually having that real radioactivity.
Thank you.
Number 41, wind noise reduction system in the IMS infrasound network.
Good afternoon, everybody. My name is Alfred Kramer. I work for the CTBTO in the Engineering and Development section. The poster is about, provides a summary of the work that was done by our group over the last 5 years in order to improve our wind noise reduction systems which are used at our infrasound stations. The main topics of the poster are the development and validation of frequency response models for wind noise reduction systems, the design and of new wind noise reduction systems with a stable and controlled response, with extended life cycles, and also with reduced maintenance cost. And as well, we try to reduce the impact on the vegetation by keeping it as much as possible available. I would like to welcome you at my poster. If you have any questions, I would like to answer them there. Thank you.
Thank you.
And that is going to be our last preview from Xenon International, a new capability for radio xenon measurements.
So we just heard a couple talks about the next generation xenon systems, the Spolix and the Sana. PNNL has built a radio xenon system also. We started from the ground up to make the system as small as we could and to get as high a sensitivity as we could. As what you see in the picture is actually the full system with a UPS and a nitrogen generator, so you have no consumables in the field. Our goal was to be able to process samples every 6 hours. We collect about 6 cc's of xenon. We're in the test phase right now. We've partnered with Teledyne Brown Engineering, and you can see their booth out just around the corner. We built 2 systems. Teledyne Brown built one, PNNL built one. We've gone through operational performance testing, where we've tested over 150 requirements. We've gone through operation verification testing, where we've tested equivalency of the 2 systems built across the US in different locations. And we're starting up the field test. In fact, next week, we'll ship the system out to RN75 to run side by side next to the Sana system. And we'll be there for 1 year at the request of the PTS to get a full year of testing. Come see the poster, and I'll describe all the testing we've done and our performance to date.
Thank you. So thank you very much. As you, there is a last one, so we don't have 40? 40, okay.
I'll just talk briefly.
Okay, please talk.
Okay, so we've talked a lot. I'm Ferenc Nakavash. I'm a scientist in residence in Monterey. So we've talked a lot about seismic detection, but there's actually other particles that come from nuclear explosions, which are neutrinos or antineutrinos. So we've done some research with my collaborators, Rachel Carr of MIT and Adam Bernstein at Livermore, and we've kind of looked at this problem, in particular with the cueing that you get if you have a seismic detection. So it turns out that the backgrounds are much lower. So the results are kind of interesting, so come to see my poster. It's P40.
Thank you. Okay, any other presenters? No? Okay, so I think that ends this session. And as you could see, there is a lot of interesting poster. We have the poster session starting in 15 minutes, so please go there, interact with the authors. I would like to thank all the authors and also my 2 conveners. Thank you very much.